Welcome, Lecture 34. This is Math 141. We are a little past the halfway point in this course. If you look around today in the classroom, we are somewhat depleted today. NC State had a football game last night, a Thursday night football game, and despite repeated requests, I was not canceling class today, so because we're not caught up. So we are having class today, but we are somewhat depleted. Maybe they will catch the cable TV broadcast at some point in time on channel 18. Yes, yeah, that was wishful thinking. One of the problems we did yesterday, I would like to go back to and kind of finish it up. We did we found the critical points. We found where it was increasing and decreasing. Actually, we didn't find the critical points. We found the critical values for x. I'd like to finish it up by finding the critical points and putting that together with where things are increasing and decreasing and get a fairly accurate sketch of that. So this was our function. And this is from third section, chapter 4. We'll hopefully wrap that up. I think that should not be a problem today to wrap that up. So here was the fourth degree polynomial. This problem is made a lot easier. I don't know if you realize that, because it has a fourth degree, third degree, second degree, and because there is no linear term, that actually makes the first derivative a whole lot easier to work with. First derivative was 12x cubed minus 12x squared minus 72x. We set that equal to 0. We were able to factor a 12 and an x because we didn't have an x term. In the original problem, the derivative did not have a constant. Therefore, we could factor out a 12x. X squared minus x minus 6 equals 0. And we were able to factor the quadratic trinomial, x minus 3, x plus 2. So we did that yesterday. I'm going a little quickly through it. We determined that at x equals 0 and 3 and negative 2, those were critical numbers that caused the first derivative to be 0, and that those would be places where the graph is instantaneously flat. It's not headed up, nor is it headed down. It's just kind of instantaneously, the tangent lines are horizontal. Here's part of the reason I wanted to go back to this. We made our chart. My chart was kind of cluttered. That's one of the reasons that I wanted to redo this, because it was at the bottom of the page and everything was kind of condensed. Take these three values and space them out on your number line so that, what was that? That was interesting noise. So we'll take negative 2 over here and 0 here and 3 here. So we've then got some space to write down. I apologize that it was cluttered yesterday. We know what the derivative is at these three values. We know the derivative never would be undefined, so we don't find a value there. So at these three values, derivative is 0. And then we picked a test value. We did the derivative at negative 3. We did the derivative at negative 1. The derivative at 2. And the derivative at 4. So all we care about is the SIGN sign. Is it positive or is it negative? We found out that this was negative, which means the function is decreasing. Hopefully this is a little more legible than what I had at the bottom of the page yesterday. The first derivative at negative 1, if you basically just plug it in here, here, and here, we want the sign. It was positive. That means the function is increasing in that region. First derivative at 2 was negative. Means the function is decreasing. And we were about running out of time yesterday. We got this as positive. So the function was increasing. All right, so let's take this chart together with the critical values of x, and let's go ahead and find the critical points and apply this stuff, the increasing, decreasing stuff, see if we can get a fairly accurate sketch of this. So I'll need some calculator help. We need the f of 0. I don't think I need calculator help for that one. The f of 0 is 1, right? Somebody needs calculator help on that one. The f of 3, let's put that back into the function. Everywhere there's an x, we'll put in a 3. Somebody run that through your machine. And we will also do the same thing with negative 2. 3 times negative 2 to the 4th. 4 times negative 2 cubed. 36 times negative 2 squared plus 1. Somebody said the f of 3. Casey? 28. Anybody else get 28 for the f of 3? Somebody try negative 2. We'll plot these points and apply this stuff right here. Move on to the next one. Anybody else? 28? Okay, 28 it is. Okay, whether it's right or wrong, you got 28, Casey. We're going with it. Okay, how about the f of negative 2? So it'd be 3 times 16 plus
I put mine in my y
-8.
equals and did the table of values, and I plugged in 3 and got negative 188.
I'm getting negative 188.
negative 188?
That's
Okay,
what I got.
we better not go with that
Yeah.
one. Okay, negative 188. All right, Casey.
You had the 8 right.
Okay, so we're minus a negative here, which is plus 32.
Negative 63 for that.
Negative 63? Yes?
Yeah.
Okay.
Get off.
It's all right. We still like you, Casey. All right, so we have these points. Let's see if we can put all this together. 0, 1. We know the graph is flat at that point. 3, negative 188. Put that way down here. Graph is instantaneously. Do you think we would have been able to figure out at some point in time that 28 was wrong? Probably, and how would we have figured that out? Because the graph would need to decrease to get to this point, and we would have the picture having to increase, so something would have told us to check that again. And what else? Negative 2, negative 63. So somewhere in here. That look right? And those are places where the graph is instantaneously flat. So we have our critical points. Zero, 1, and 3, negative 188, and negative 2, negative 63. And we found them by setting the derivative equal to 0, so we know they are horizontal tangent lines. All right, the rest of this then is to apply our chart. Move this down, see if I can bring the chart back in. So there's our chart. We know on the other side of negative 2, here we are at negative 2. Here we are at 3. So on the other side of negative 2, we've got to have a graph that is decreasing, right? So we're going to decrease into here and then become fairly flat at that point. Now the rest of it kind of takes care of itself for a little while, but we do have some backup. The graph at this point is supposed to increase. Well, it has to, because how do you get from here to here? You've got to increase. Leaves here fairly flat and enters here fairly flat. The next thing it's got to do is decrease, which certainly it has to get from up here to down here. Leaves here fairly flat enters here fairly flat, and the last thing it's going to do, which we don't have any indicator of on our graph, is it's got to leave here fairly flat, but we know that it increases. So the graph looks something like this. Now that's rough. Actually, that's probably not good terminology. That's probably better said that it's a sketch as opposed to a graph, because I don't know any of these values from my picture. I don't know the 4 places where it crosses the x-axis. If I knew those, it would probably upgrade from a sketch to a graph. I think the instructions on this were to find maximum, minimum values. Do we have any relative max, absolute max, relative min, absolute min?
Relative max. 0, 1.
Okay, relative max right here. Is that an absolute max?
No.
No. In fact, this doesn't have an absolute max. Is that correct? Relative min, is that correct?
Yeah.
Is that an absolute min?
No.
Nope. Relative min,
Yeah.
absolute min.
Yeah.
Yes. So this particular value, negative 188, is the lowest value, the smallest value you'll ever get out of this function for any x value you want to choose. So we've got a relative min, a relative max. This is a relative min and an absolute min, and no absolute max for this function. Questions on that?
If it had a 4th point of inclination, or when it would flip again, would that mean that that would not be the absolute minimum because it could potentially
Right.
dip somewhere else?
Right. So if this, let's say, turned up here and kept going down, then this would not be an absolute minimum. But let's keep in mind some things that we have a pretty good feel for this being the correct answer. What was the original polynomial? 4th degree, right? How many roots does a 4th degree polynomial have? It has at most 4. I mean, sometimes it has repetition, but this one doesn't have any repetition of roots. So 4, and what did we say about changes in direction? It would be 1 behind that number, so we've got 3 changes in direction. There's 1, and there's 1. So we're not going to get this out of a 4th degree polynomial. All right, okay to leave that one? I think that one is kind of to a point where we've done everything we can with regard to what we're studying in this chapter. I do want to backtrack, and we did the mean value theorem, but we didn't do a problem with the mean value theorem. So unfortunately, there are not any good ones in your book. So I went to another source. So let's do a mean value problem, and then we'll throw in the second derivative stuff, and then we'll go on about the rest of our lives today. Mean value theorem. I suggested the way to remember it was that the slope of the secant is equal to the slope of the tangent. Well, the slope of the secant, the slope of the tangent. So that's the derivative at some value c hopefully somewhere between a and b. And so this is the slope of the tangent. And then that's supposed to equal the slope of the secant at that single value c. Slope of the secant would be the difference of the y's over the difference of the x's. So let me read these directions, and we'll apply these directions to this problem. Determine whether the function satisfies the hypotheses of the mean value theorem on the indicated interval, and if so, if it doesn't satisfy the hypotheses, we can stop there because it's not necessarily true. But if it does satisfy the hypotheses, some of you are thinking, what in the world is that? Find all numbers c in the open interval such that that is true. So there might be a c value, there might be multiple c values, but the theorem, if the hypotheses are met, the theorem guarantees at least one C value. So what are the hypotheses? What has to be true in order for the mean value theorem to actually have a solution?
Continuous.
It's got to be continuous. And it's got to be differentiable. So we don't want any of those corners or cusps or any kind of a break in the graph, any of that stuff. That's going to mean that there is not necessarily a C value. In fact, there probably won't be. But if we can determine that it is continuous and differentiable on the closed interval, right, then we're in business. So the problem, I'll just pick a kind of a simple one. You know what? Let's pick one that's a little tougher. I've been accused of picking the easy one, so let's pick one that's... I don't like being accused of those things. 3x to the 5th plus 5x cubed plus 15x. And the interval is -1 to 1. So supposedly there is a value somewhere between -1 and 1 such that the derivative at that point is the same as the slope of the secant line that connects these 2 points on the curve. So, hypotheses. Before we search for this number, we really need to know that the search is going to get us somewhere. Continuous?
Yep. Okay.
Why is this continuous? What would suffice as a reason? Polynomial. So all polynomials are continuous. They're also smooth in a sense that they don't have any abrupt changes in direction. How about differentiable?
Mm-hmm.
Does the derivative exist at all values from -1 to 1? In fact, the derivative exists at all values, right? So not just necessarily this interval. And that's probably, again, related to the fact that it's a polynomial, right? It is differentiable. So we can find a value, at least one value. So the derivative, let's go ahead and find that. We're going to need it. The derivative as a function of x is what?
15x
Plus
15. I mean,
X squared.
x squared
plus
plus 15. Okay. Casey, everything all right today?
Yeah, maybe.
All right, so we need the derivative. Actually, if we're going to kind of follow exactly the mean value theorem, we want the derivative at c, right? So that'd be 15 c to the 4th plus 15 c squared plus 15. And the derivative at c, and we're searching for c, or c values, possibly several of them. What do we want over here on the right? The f of b, f of 1, right? Minus the f of -1 all over 1 minus -1. So there's the mean value theorem for this particular problem. Yeah, this is a pretty good one. Yeah, I had one picked out that was a whole lot easier than this, but this is a good problem. Anything we can do on the left side?
Factor out 15.
15, that'll help, I think. What is the f of 1? 3, 8, 23? What's the f of -1? -3, -8. Okay, so this must be an odd function. Is that correct? Right, for that to be true? for the f of 1 to be 23 and the f of negative 1 to be negative 23. It is an odd function. 1 minus negative 1 would be 2, so we're getting there. I may go back on that factorization. We may bring it back into this form. May or may not be helpful, but it's okay. We can bring it back. So what? 46 over 2, 23? Here? I think I'm going to go back to the version before we had 15 factored out. Any reasons? Anybody see why that might be helpful?
Subtract.
So we can get everything on one side, 0 on the other. So there's our equation. We're going to try to solve that equation for C, maybe multiple values of C. And we want to find C values that are not negative 1 and not 1, but somewhere between those two values. So we'd probably want to put everything on one side and 0 on the other. Move this. So we are going to have 15c to the 4th. If you leave this in terms of x, that's fine. Then just realize that the x value you find is the c value that you were looking for. So if we subtract 23 from each side, what do we have? Minus 8 equals 0. Now, hopefully, this thing will factor. I don't know. Let's see. That would be very nice if it factored. We could use the quadratic formula eventually, but we're going to have to do a little substitutions before we would do that. Any way we can get 15c to the 4th? Well, if I make this a c squared and c squared, then I can get my c squared in the middle. So I'm going degree 4, degree 2, degree 0. So that has a chance of factoring. We're going to need factors of 15 here and here, and factors of negative 8 here and here. We can just try some values. Factors of 15, 5 and 3. Let's give that a whirl. And this will probably be the determining factor. The choices for factors of negative 8. 1 positive, 1 negative, right? Because we've got to get a negative 8. Looks like the positives are going to outweigh the negatives by 15 when we get the middle term. So if we were to try 4, 2, that's not going to work. Is that right?
That's right.
So if we would put 4 here, that'd give us 20. And 2, minus 2 here, that'd give us, that wouldn't work. Any possibility 8 and 1 would work? We want this to factor because it's not going to be pretty if it doesn't factor.
Well, it don't matter.
I don't think it does. Not factoring?
Nope.
Any way we could use, instead of 5 and 3, we could use 15 and 1?
It's worth a try.
It's worth it.
It's not gonna work.
It doesn't work.
Oh, maybe it's
Not working, right? Not factoring? All right, so we've got apparently a 4th degree polynomial. Right, so let's do a substitution that will make it look like a 2nd degree. So if that is the case, we've got 15c to the 4th, which is really 15c squared squared. Has a problem required us to do this in this course yet?
No.
Okay. Here we've got a 15c squared and then a minus 8. So let's let u, or something else, some other letter, temporarily take the place of c squared. And if we do that, c squared squared really becomes what? U squared. And 15c squared really becomes 15u. And we took a fourth degree. Not every fourth degree can you do this, but you can do it when it goes from degree 4 to degree 2 to degree 0. This will work. So we know it's not going to factor, so let's go right to the quadratic formula, which solves for the variable that's being squared, which in this case is u. So how's that going to look?
E squared
Negative 15
plus 9
plus or minus
B.
b squared 15 squared 225
Yeah.
minus 4 times a times c
120, 240.
all over twice a
What's the first one? Negative what?
Negative.
negative b.
Negative.
There's b. Negative b plus or minus b squared minus 4ac all over twice a. So I told you that it was going to be better if it factored. So we're kind of having to do battle now because it didn't factor. We're going to be minus a negative, so we're going to add this on. And this looks like 60 times 8, 480. 225 plus 480. What is that?
705.
705?
Yup.
Not a perfect square, but can we pull a perfect square out of there? Any perfect squares that are factors? Let's just get a decimal approximation. This is our u value. Remember, that's not our final answer because u was representing what? C squared. So we're going to have to go back, and once we get a number, remember this is c squared. So what is negative 15 plus the square root of 705 all over 30? Agreement? 26.55?
Yeah, 2.
Now, let's go ahead and, this is part of it. What's negative 15 minus the square root of 705 all over 30?
-1.385.
Negative
1.385. Or something like that. Hold on. I don't really know.
7.
You know?
Okay, do I really need to write anything else down? It's negative, isn't it?
Yeah.
Minus 15 minus the square root of 705. That's a negative numerator. We're going to divide it by 30. Isn't it negative?
Yeah.
So it's negative some number. I don't care what the number is. Why do we not need that number? Because what is u in this problem?
Square.
It's c squared. Are we going to be able to square c and get a negative number? No. So it doesn't really matter what this is. It's negative. Now, is this number correct?
No, that's
No.
the
No?
square.
That's
That's
the
the value.
Oh,
of
that's
the
the square root of 705? Okay. So we need to subtract 15 from that and divide it by 30.
0.385.
What is it?
0.385.
0.385. Okay.
And why'd you say we don't need the negative one?
Because u is temporarily representing c squared, and we're really searching for c,
Right.
we're going to, where there's a u here, we're going to put in a c squared.
Right.
C squared equals a negative number. Not going to happen. But c squared equals this. That is very possible. So in fact, that's our next step, where we have u in this equation. U was a representative of c squared. Are we going to have two possible c values? Remember, we're searching for c in this interval, right? So are there two values, two numbers that we could square and get 0.385 that are in here?
Plus or
plus or minus, right? We're doing the taking of the square root, so we have to allow for both possibilities. What is the square root of 0.385? Thank goodness for calculators. 0.6205. So do we want them both?
Yeah.
They're both in here, right? So the directions or instructions were to find all the c values in the closed interval such that the first derivative at c, you kind of have to go way back to where we started the problem. So we have those two c values. Apparently the derivative at these values is the same as the slope of the secant line that connects the 2 points, -1 something and 1 something. So we really have a C1 and a C2, both of which are in here. All right, don't ever accuse me of not taking the more difficult problem and show it as an example. So that's a pretty lengthy mean value theorem problem. All right, the rest of this section, any questions before that gets moved?
We never figure out a question again.
You just, if we had a picture, let me see if I can resurrect a picture. What are the points? 123. Let me just take a few seconds to. (123) is one of our endpoints, and -1, -23 is the other. So we've got this segment that connects those 2 points. We know that at 2 places on this graph, this 5th degree polynomial, 2 times between -1 and +1, 2 times the slope of the tangent is exactly the same as the slope of this dotted line. So it'd be parallel to it. And in fact, we know where that happens. It happens at about 6/10 positive. To be real accurate, we could go back, and I'm not going to take the time because I know what we have yet to do. We could plot these points. We don't know that right now, nor do we know this. But if we were to plot the points, this is a strong possibility of what could happen. So at 0.6, we're up here, let's say, and at -0.6, we're down here. Let me look at this equation, original equation. Okay, so it does go through the origin. So let's say the graph looks something like this. We know at these 2 points that we found, 0.6205 and -0.6205, the slope of the tangent is the same as the slope of the secant. That's really probably not some major revelation, but that's what we do know from this problem. All right, second derivative information. Let's go on to that. So first derivative gives us increasing, decreasing, where it's potentially real flat and where it's potentially real steep. Second derivative information tells us about concavity. And I hope I have a sheet that would, here we go. Concavity really tells you how it is increasing or how it's decreasing. Is it getting steeper as it goes, or is it getting flatter as it goes? So second derivative information is going to give us this kind of data. So a function or its graph is called concave upward. If the derivative, so I'm going to draw a picture in a second, but the derivative would have to be increasing. And it's concave down if the derivative is decreasing. there may or may not be a WebAssign question with that kind of information in it, but that's in essence why it has the shape that it has. The test and what they call the second derivative test, those are pretty straightforward. But here's what they mean by the derivative increasing. So let's say we've got a graph that looks something like this. So we look at the slopes over here. These slopes are negative. This slope is a little bit larger, less negative. This slope is 0. This slope is maybe positive 1. This slope over here is positive 3. So from left to right, the slope is negative 3, negative 1, 0, 1, and 4. What's happening from left to right to the slopes? They are increasing. The slopes, not the function itself, because the function was decreasing, then flat, then increasing, but the slopes are increasing. And if the slopes are increasing, it has to have this shape. It's the only shape it could possibly have where the slopes are increasing. And what is this shape called? Concave up. Wonderful abbreviation. C up, which is kind of what it looks like, right? Kind of looks cup shaped. We don't have that nice abbreviation with the other one, but we do have it with this one. So if the slopes are increasing from left to right, it has to have this shape. Similar fashion. We've got a curve that has that basic shape. So analyze the slopes. The slope here, let's say, is 4. The slope here is 1. The slope here is 0. What's happening to the slopes thus far as we go from left to right? They're decreasing. Then the slopes get negative, and then they get even more negative over here. So the slopes are decreasing. So if you read this graph like you read a page of prose from left to right, the slopes are decreasing. It has to have this kind of shape. And what kind of shape is this? Concave. Yeah. Okay. No nice abbreviation for this. So that's how those shapes are determined. Let's go back to this chart. Concavity test. Okay, I think we kind of just validated this. If we want to determine what the function is doing, we use, in terms of increasing, decreasing, we use the derivative. If we want to know what the derivatives are doing, we use the derivative of the derivative, which is the second derivative. So if you know all your first derivative stuff, all you basically do is have to take the derivative of each side, and you've got the second derivative information. So if the second derivative is positive, the graph is concave up. And if the second derivative is negative, it's concave down. So how do you actually do a test? You want to check where the second derivative is 0 and where the second derivative is undefined. These are not, unfortunately, they're not called critical points. Critical points refer to the first derivative. This is second derivative. Doesn't really have a specific name. It's just places where the second derivative is 0 and places where the second derivative is undefined. That's what we're searching for. So the same. Well, these are possible. Points of inflection. Thank you for bringing that term up. What will actually determine if they are, in fact, points of inflection? It's got to change concavity there. So we can have a possible point of inflection where, in fact, it does not change concavity, and it is not a point of inflection. Let me give you a quick picture of how that might happen. So we do all our first and second derivative stuff, and we come up with a graph that looks something like this. This piece of the graph is concave up. Here's our possible point of inflection. Is it a point of inflection? I don't know until I actually check it out on both sides. This is also concave up. So is that possible point of inflection in reality a point of inflection? It's not. So it did not change concavity. So there's what we ask ourselves. Did it change concavity there? Absolutely not. So it's not a point of inflection. If it does change concavity, and it was a place where the second derivative was 0 or the second derivative was undefined, so let's say the graph looks like this. Now we do have a point of inflection. This is concave up. This is concave down. Here's our candidate. It actually is a point of inflection. It did change concavity at that point. So this is a point of inflection. So we'll list them, initially we'll list them as possible points of inflection, and then as we continue with the problem and we determine concavity, then we'll see if in fact it is. All right, let's take a look at time for one example. Let me have to choose between these two. I'll pick the more difficult one since that seems to be the trend today. So there's our function, x to the 2/3. And let's see what we can find out. I hate to do something that's not a polynomial. Let's save this because of the time. We've got like 4 minutes. We'll do this problem, but not as our first problem. Probably best to start with a polynomial. Derivatives are easier. Then you've got your little first derivative chart, second derivative chart. Those are a little easier. So first derivative is and we would go ahead with the first derivative and find out where it's increasing and decreasing and all that stuff. Find the critical points. First derivative will never be undefined. So I think we know what to do right here. That's not what we're about today. We are about the second derivative. So let's move on. We would eventually certainly want to have all this information to get our graph. Let's go with the second derivative. Second derivative is (30x). So we would do our second derivative search, which is setting the second derivative equal to 0 and seeing where the second derivative is undefined. Well, we don't have to see where it's undefined. It's a polynomial. So any recommendations on making this a little bit easier to solve? 10x. That leaves us with
2x squared minus 3.
So we've got one easy and obvious value that causes the second derivative to be 0, and then we can get two values out of this. Can I treat that as the difference of two squares? I guess more importantly, can you treat that as the difference of two squares? Is this something squared? It is. It's the square root of 2x, right? And is this something squared? Square root of 3. So this is kind of a squared minus b squared. Not a delightful a, not a delightful b. So it ought to be a minus b times a plus b. Now we've got our three possible solutions. X is equal to 0. That's kicking out a possible point of inflection. How about this first one? Square root of 3 over square root of 2, right? Which is square root of 3 over 2. And the negative of that? So if we were making a chart, which is about all we have time for, we'll pick up and kind of finish this problem. But the new stuff, today's stuff, we would be making a second derivative chart. Your chart doesn't have to be exactly like this chart, but somehow that you can determine if and when it changes concavity. So 0, negative, shouldn't that be all over 2? What's a good decimal approximation for square root of 3 halves?
1.22.
1.22? And positive 1.22. So that'll give us an idea where we are on the number line. So what do you think is the task from this point?
Figure out
Plug
if
in
it's positive and negative.
Okay, see where the second derivative is positive and negative. That'll determine concavity. So pick a value to the left of negative square root of 3 halves. So there's where we are. How about negative 2 or negative 3? We would pick a value between these two. Negative 1 is in there. Pick a value between 0 and this value. Positive 1 is in there. And pick a value larger than square root of 3 halves. Looks like 2 is out there. We've got time to do this, and we can stop. If we put negative 2, here's our factored form. Actually, let's go back to this form. That might be a little easier to work with. There's the second derivative. So if we put negative 2, that would make this one negative, right? And negative 2 in here makes it what? Positive. So negative times positive is negative. What's that tell us about the graph? Not decreasing.
Concave down.
Concave down. Let's put negative 1 into the second derivative. It makes this term negative. What about negative 1 in here? Negative, right? Negative times negative is positive. Function, concave up. So what do you think? Possible point of inflection? Yes. It changed from concave down to concave up at that value, this value. Derivative at 1 makes this positive, makes this negative. Positive times negative is negative. The function is concave down. Another point of inflection, right? And the derivative at 2 makes this positive and this positive. The product of the two is positive, which makes it concave up. So that makes this another point of inflection. Okay? We'll dress this picture up, but that's the new information from this section. Have a great weekend.